Hey, I'm Alex Teal. I'm the Chief Software Architect here at Urban Machine, and today I'm going to show you how we've built and rebuilt our AI vision pipeline over the years to salvage construction waste. Spoiler alert, it wasn't always easy, but the lessons have been worth it. Let's jump right in. Before starting Urban Machine, I founded an AI vision startup called Auto. Over the years, we developed and deployed AI models across 30 unique use cases, parallel processing, scalable pipelines, you name it. That experience taught me a lot about what works and what doesn't work when scaling AI systems. And trust me, reliable pipelines are everything. For example, take a look at Google's paper, High Interest Credit Card of Technical Debt. If you haven't seen it, this paper is hilarious, but also very true. You have to be careful about how you implement these systems. Not just the model, but everything surrounding it. You can't half-ass infrastructure. A weak pipeline cripples your ability to iterate and improve, and that's the death knell for AI. This is our very first robot here. We threw it together in under 1 month to start exploring the problem space. We chose the Azure Connect 4 over the Intel RealSense because it could see the thin features of nails slightly better. When I first started developing our vision pipeline 3 years ago, we thought, let's just use cheap 3D cameras and detect everything that sticks off the surface of the wood. After all, nails are sharp pointing objects sticking off the surface. How hard can it be? Well, first of all, we were actually wrong. A lot of nails were flush to the surface or folded over. But also, the cheap 3D cameras had a really hard time even seeing thin objects like nails. So we took the learnings from our first prototype and we created a second one in a span of a few months. This one had a big feature called the rake. The idea was, hey, what if we could remove nails without any vision pipeline, just with dumb, stupid motions? The other thing we did is we seriously upgraded our camera. We upgraded to a Zivid, which is not a cheap camera. I'm talking about 12 grand here. By this point in time, I was familiar with the state of the art on running inference and detecting objects directly on 3D point cloud data. I decided that that was going to be too expensive to label and it would hamstring our ability to quickly iterate and add data to the data set or change camera angles or anything else that we wanted to do. So instead, what we did is we used more conventional 2D instant segmentation algorithms, and that let us operate in the 2D image realm, which is good because either way, we're going to have to run inference and detect on 2D planes because sometimes nails are folded flat on the wood. The benefit of this is that it let us get started really quickly. We hired a labeler who would take batches of images, label them, and then we would train models overnight. This is about the point where we started building out our cloud data pipelines. So we worked out most of the kinks in the vision system and built a third machine. This is the first machine that actually left the shop and got deployed to real-world locations to be able to clean wood on the field in the construction site in a dirty environment. We soon ran into an issue with the Zivids. The problem with the Zivids is that they use structured light in order to capture that 3D point cloud. If you're not familiar with structured light, what that means is it projects this 3D pattern onto the surface and uses that to figure out the 3D shape of everything in the image. One big issue with that is if your object is moving, you're going to get crazy noisy data. So we could only do quasi-static scanning, where we move, stop, take a picture, move, stop, take a picture. In the early development stages, that was okay because it let us move really quickly. The camera was easy to use, it worked really well, and got us good quality data. But later on, we had to switch to something that could let us scan 3D point clouds while the object was moving. Let's dive a little bit deeper into the actual vision pipeline. Now, you might be looking on screen and wondering, hey, how is it that they're coloring all of the nails in 3D? I thought this was supposed to be a 2D instant segmentation model. Well, that actually doesn't stop you from getting 3D data about the nails. What we did is we took an instant segmentation model that produced high accuracy segmentations of all the nails, the types of nails, the heads, the bottoms, all the classifications of each nail part in the image, and we apply it to the 3D mask that we're getting from the cameras. That way, we get 3D point clouds representing the shape of every unique nail in the image, and we know which points belong to which nail. To summarize, at this point in the process, we would start out with an image, run instant segmentation, find the nails, get the 3D map for those nails, run all types of vision pipeline processing techniques to figure out the head from the tail, where the best pick points, how to orient the gripper, and pass all that information off to robots, which would then execute those moves and then check again with the camera to see if they need to adjust. In that time, we built a whole nother robot, deployed to more pilots, and learned a lot. It became clear that 3D cameras were just not going to cut it, even if we could scan while the wood was moving. We needed to try something drastically different. So we did what we always do. We re-architected the whole system. We took our learnings from the last system and added 2 more processes, the most important of which was the cutter. The cutter is basically 2 bandsaws that come in close to the wood surface and cut all the fasteners so they're flush to the wood surface. That had a huge impact on what we could do with the vision pipeline. First of all, we could get cameras super close to the surface of the wood without worrying about nails scratching them. Second of all, we could treat the wood as if it was just a 2D plane. And if the wood is a 2D plane, we can use 2D cameras. And if we can use 2D cameras, we can buy cheaper industrial cameras that run at high frame rates and let us scan the wood much faster. Faster scanning means faster wood speeds, which means faster throughput at the machine. These days, our AI pipeline is almost entirely automated. It starts with our robot in the field, scanning, finding images, taking about every 10 centimeters of wood and saving an image. Then it corroborates that with other sensors, for example, camera on the infeed versus the camera on the gantry. Did it actually detect a nail when it went to grip it? Things like that. Then we have a system to asynchronously upload that data to the cloud when there's internet available. There's an automatic pipeline that triggers that uses entropy-based methods to basically figure out, hey, out of the 10,000 images we collected over the last few days, what are the best ones that would help reduce the entropy of our model? Basically, which ones would give the most information to have a human actually label it? Then that gets piped over to our labelers who label the images. And once a certain threshold is met, that triggers a retraining. But we use Google Cloud as our training platform. We train our new model, that gets regression tested, and we can update that field model remotely. And then the process starts over again. Thanks for watching, folks. That's all I've got to show for you today. If you like the video, please subscribe, like, give a comment, add me on LinkedIn, send me an email, whatever it takes. Definitely drop something in the comments if you want to see something specific that I didn't show in the video. I'm going to try to keep posting interesting robotics content so that maybe other people can enter the field and not make the same mistakes that we did along our way. Awesome. Have a good one.